Hello everyone. Today we're going to look at limits. Before we can talk about what a limit is, we need to discuss continuity. A function is continuous at a point if A, the function exists, and B, any small change in x produces only a small change in y. So we're going to look at some examples using graphs. So our first function here is a parabola. Whoops. And if I take any point on this function, say this guy right here, and then I move a little bit in the x direction, so I move a little bit to the right or a little bit to the left, then I've only moved a little bit up or down in the y direction if I stay on my graph. So if I move a little bit to the right, I've only moved a little bit in the y direction. If I move a little bit to the left, I've only moved a little bit in the y direction. This parabola is what's called continuous everywhere. If I look at this function over here, and I take a point over here, I can move a little bit to the left or a little bit to the right, and again I've only moved a little bit up or down. However, if I take a point over here, and I move a little bit to the right, I've moved very far up to find my y value. So this function is not continuous at 0. And in particular, the function doesn't even exist at 0. So this is a graph of the function y over x. If I look at any place really that's not 0, and I move just a little bit to the left or right, I'm fine. But if I look at 0, and I move a little bit in either direction, I'm either really far down or I'm really far up. So this function is not continuous at 0. I'm going to move this up a little bit so we can see it a little better. If I look at this function over here, I can look at any point over here and any point over here, and if I move a little bit to the left or a little bit to the right, again I've only moved a little bit up or down. However, if I look at where this open circle is, now remember, an open circle means that point is not actually there. Everything up to it is there, but that point itself is not there. So if I looked at, say, 1.99999, and I'm right here, and I move a little bit so that I'm past 2, I have to jump up all the way up here to find my new y value. So I moved a little bit in the x direction, but I moved a lot in the y direction. So this function is not continuous at x equals 2. If I move over to my last function, again, if I take any of these points over here, or any point down here, and I move just a little bit in the left, in the x or y direction, then I've moved just a little bit in the y direction. And actually that's true along any of these points. However, in order to be continuous, my function again has to exist. And this open circle here shows that the function does not exist at x equals 1. Since it doesn't exist at x equals 1, it cannot be continuous at x equals 1. One of the really nice things is if we're looking at continuous functions graphically, then there's a nice shortcut to determine whether or not the function is continuous, and that is, can I draw the function without lifting up my pencil? So if I had a pencil and I wanted to draw over or trace my function as I move from left to right, if I can do it without lifting up my pencil, then it's continuous. So if I go back to my parabola and I start tracing it, I can do that entire thing without lifting up my pencil. And that is one way to show that my function's continuous. And I'm just going to clear this out a little bit. So if I just erase, whoops. Oh, that's not working. Alright. If I start with my other function, my 1 over x, I can start tracing it. And I'm fine, I'm good. But if I want to continue past 0, I have to lift up my pencil to start tracing over here. So since I had to lift up my pencil, my function is not continuous. The same thing for my third function. I can start tracing it and I'm fine, but then to get up to the other part of my graph, to get up here, I needed to lift up my pencil, so it was not continuous. The same is true with my last one. I can draw all the way up to here, but then there's nothing there. I have to jump over it, so I have to lift up my pencil before I can start graphing the rest of it. So again, when you graph your function, if you move from left to right, if you have to pick up your pencil, then it's not continuous. So then let's think of what type of functions are continuous. All polynomials are continuous. All rational polynomials, which is a polynomial divided by a polynomial, are continuous everywhere that does not make the denominator 0. And even roots of polynomials are continuous everywhere the polynomial is non-negative. If we look at an odd root of a polynomial, that's continuous everywhere. The even roots have to make sure that what's inside is non-negative. So here are a couple of examples. So 3x to the fifth minus 5x cubed plus 9x squared minus 1 is a polynomial. Remember that polynomials are sums and differences of terms that look like a number times x to a whole number. 5, 4, 2, 1, 0, things like that. Here's a rational polynomial, 3x minus 7x cubed plus 1 divided by x squared minus 1. This is continuous everywhere except x equals 1 and x equals negative 1, which are the values that make your denominator negative, 0. So remember, you cannot divide by 0. So as long as the denominator is not 0, you're good to go. Another example, the square root of x minus 3. So this is an even root of a polynomial. It's continuous for any values that are bigger than or equal to 3. So the values that make my denominator non-negative. But now let's get into limits. So the limit is looking at what happens as a function approaches a particular x value, but not what happens when x is that value. So I don't care what happens when x is 2. I care what happens as x gets closer and closer to 2. So as an example, what happens to the function 2x plus 1 as x approaches 2? We write this as LIM, short for limit, and then below the limit is x, your variable, an arrow, and then 2, the number that we're concerned with, and then in parentheses the function. So this is said as the limit as x goes to 2 of 2x plus 1. So we don't know anything about limits yet, so if you don't know anything about what you're looking for, you should make a table. Just like if you don't know how to graph a function, make a table. So again, I want to know what happens to my function as x gets closer to 2, so I'm going to look at values that get closer and closer to 2. We're going to have 2 tables here because you can come to 2 from 2 different directions. So my top table is getting closer and closer to 2 from numbers that are smaller than 2. The bottom table is getting closer and closer to 2 from numbers that are bigger than 2. And as we look at the f values, we've got 3, 4, 4.8, 4.98, 4.9998, 7, 6, 5.2, 5.02, 5.002. And you want to look at that and say, well, does it look like this is actually going to a single number? So what if I did 1.999999, 2.0000001? Will they get closer and closer to a number? And if you look at the values, it looks like they're getting closer and closer to 5. So we would guess that the limit as x goes to 2 of 2x plus 1 is 5. That's the best we can do. We can guess that it's 5. We don't know for a fact that it's 5 just yet because we're just getting closer and closer to 2. It could actually be 4.999. It could be 5.00001. but we're going to guess that it's 5. And also, if we notice, if I plugged into f of 2, I do get 5. That's not always going to be the case, though. So let's try another one. Let's look at the limit as x goes to 2 of 2x squared minus 3x minus 2 all over x minus 2. Notice that f of 2 is undefined, so I can't just plug in 2 and then be done with it. But what I can do is, again, make a table. So I've got the same x values, x getting closer to 2 from numbers smaller than 2, and x getting closer to 2 from numbers bigger than 2. And then I've plugged in f of x, and I get the following: 3, 4, 4.8, 4.98, 4.998, and then 7, 6, 5.2, 5.02, 5.002. And again, it looks like it's approaching 5. This is getting closer to 5. This is getting closer to 5. Again, I can't prove that it is 5 at this moment, but we're pretty confident that it's 5. And then the next question is, well, why do these two functions have the same values? If you look back at the two tables, they were the exact same values. And that is because of the following. If I look at 2x squared minus 3x minus 2 over x minus 2, and I think back to what I had to do in Tech 1, I would have had to factor this and see if I could simplify it. So I'm going to factor the top. And the top factors into 2x plus 1 times x minus 2. And then again in Tech 1 we said, well, these two things cancel, and I'm left with 2x plus 1. But there is something very particular about this. It's not always 2x plus 1. It's 2x plus 1 everywhere except x equals 2. Remember, f of 2 was undefined in this function. This function, f of 2, is very much defined. So you have to be really careful. It's not that these two things are equal. They're equal everywhere except x equals 2. And if I look at their graphs, they look very similar, except notice that there is a hole here. And again, that is because f of 2 in this case is undefined. But if we look at the graph and we say, well, what happens as I get closer and closer to 2? My function gets closer and closer to 5. The same was true here. As I went closer and closer to 2, my function got closer and closer to 5. And again, I don't care what happens at 2. So limit-wise, these two functions as x goes to 2 are the same, because I don't care what happens at 2, I just care what happens as I get close to 2. And in both cases, as I get close to 2, my function gets closer and closer to 5. If a function f of x is continuous at x equals a, then the limit as x goes to a of f of x is f of a. So knowing this, we can then say definitively that the limit as x goes to 2 of 2x plus 1 is 5, because 2x plus 1 is a polynomial, so I know it's continuous. And if it's continuous, this is now telling me that I can just plug in the value. We have another thing that's very useful. If f of x equals g of x for all x except x equals a, then the limit as x goes to a of f of x is the limit as x goes to a of g of x. And this tells us that since that ratio we saw before, that rational polynomial, was equal to 2x plus 1 everywhere except x equals 2, then the limit of that rational polynomial is the limit of 2x plus 1, which is 5, because again it's continuous. So we're going to use these two facts a lot. If I have a function that's continuous and I'm looking for the limit, I can just plug in the point. If I have something that's not continuous, but I can show that it's equal to a continuous function, except for a particular point, then I can use this second fact to show that the limit is, again, what I think it should be. So we're going to do an example of that next. Find the limit as t goes to 3 of t squared minus 9 divided by t minus 3. We're going to use some algebra to factor this. And it's a difference of 2 squares, so t squared minus 9 becomes t plus 3 times t minus 3. My t minus 3's will cancel, and this will equal t plus 3 everywhere except t equals 3. So again, at t equals 3, this function's undefined. So it's equal to t plus 3 everywhere except t equals 3. T plus 3 is a polynomial, so it's continuous everywhere. So the limit as t goes to 3 of t squared minus 9 over t minus 3 equals the limit as t goes to 3 of t plus 3, based off of this example. And because t plus 3 is continuous, I know that I can just plug in 3. So this is equal to 3 plus 3, which is 6. So we have solved our first exact limit question. So let's try another one. Let's find the limit as z goes to negative 4 of z squared minus 3z minus 4 over z plus 4. Again, we have a rational polynomial. My function is undefined at this point. It makes this guy 0. So I want to try to rearrange it. So I'm going to, again, factor the top. I want two numbers that multiply to negative 4 and add to 3. And those two numbers are 4 and negative 1. Again, my z plus 4's will cancel, and this will equal z minus 1 everywhere except z equals negative 4. So this limit is equal to the limit as z goes to negative 4 of z minus 1. And then the fact that z minus 1 is a polynomial means it's continuous everywhere, means that I can just plug in my negative 4. So I get that it's negative 4 minus 1. So again, z is negative 4, which gives us negative 5. So this one's doesn't look quite the way that it's supposed to. So this x minus 2 should be down here. So the limit as x goes to 2 of 1 over x minus 2. We cannot rewrite this fraction to be equal to another one since the numerator is a 1. I can't factor that at all. So the best thing we can do is make a table and see what happens. So again, that should be on the bottom. And it goes away again. So for my top function, again, I have x values getting closer to 2. In this case, I've got them switched. I've got numbers that are bigger than 2. The second table has numbers getting closer to 2 from numbers that are smaller than 2. And of course, that should be 1.99, not 199. And if I plug in the values, I get 1, 2, 10, 100, 1,000, negative 1, negative 2, negative 10, negative 100, negative 1,000. So do these two tables go to the same number? And the answer is no. These numbers are all positive, and these numbers are all, negative. This tells me that the limit does not exist. So that's a possibility. There might not be a limit. And again, this is very similar to that 1 over x function that we saw earlier. So as x gets closer to negative 2, it looks something like this. So in one spot, we've got numbers, oops, I got that backwards. It should be over here. But regardless, it's the same shape. So at one point, you're getting numbers that are really negative. Another point, you're getting numbers that are really positive. So there is no limit. It doesn't go to a particular number. The next thing we're going to look at are limits as x goes to infinity. Remember that infinity is not a number. You cannot plug it in, right? You cannot do infinity squared minus 2 times infinity plus 5. You can't do that. We're going to focus on rational polynomials. So we're going to let p of x and q of x be polynomials, and we're going to focus on the limit as x goes to infinity of p of x over q of x. And there are three possibilities. The first one is that the degree of p is bigger than the degree of q. Remember, the degree of a polynomial is the highest exponent in that polynomial. So if there's a higher exponent on top than there is on bottom, then the limit is infinity. If the degree of p is smaller than the degree of q, so the larger degree is on the bottom, then the limit is 0. Remember, this is only true when x goes to infinity. If it's not infinity, if it's a number, then we have to use the rational polynomial thing that we were doing before. If it's not continuous at that point, then you have to try to factor it and make it equal to a function that is continuous. And then the last case is if the two degrees are equal. If the two degrees are equal, then the limit is the ratio of the leading coefficients. Remember, the leading coefficients are the coefficients of x to the highest power in the top and the bottom. So we're going to do some examples. The first one, the limit as x goes to infinity of x to the 8th minus 3x over 4x to the 4th minus 2x minus 1. So the degree of the top is 8. The degree of the bottom is 4. 8 is bigger than 4, so the degree on the top is larger, so the limit is infinity. For b, we've got 3x squared minus 8 over 7x minus 3x to the 4th. The degree of the top is 2. The degree of the bottom is 4, so the degree of the bottom is larger, so the limit is 0. C, the limit as x goes to infinity of the following. The degree of the top is 7. The degree of the bottom is also 7. So the limit is the ratio of the leading coefficients. The leading coefficient of the top is 9. The leading coefficient of the bottom is 27. So the limit is 9 over 27, which is the same as 1 over 3. For D, which already popped up, we've got 6x cubed minus 8x plus 20x to the 4th over 7x cubed minus 2. The degree of the top is 4. The degree of the bottom is 3. Larger degree is on top. The limit's infinity. For E, the degree of the top is 28. The degree of the bottom is 30. The degree of the bottom is larger, so the limit is 0. F is a little bit trickier. We've got the degree of the bottom is 3. The degree of the top is also 3. We have the square root of x to the 6th. Remember, the square root of x to a power, we need to divide that power in 2. So this will be 4x cubed. Square root of 16 is 4. Square root of x to the 6th is x cubed. So the degree on the top and the bottom are both 3. The leading coefficients are 4, again, the square root of 16 over 3. So the limit is 4 over 3. So just be careful if you've got a root in there to make sure that you're actually doing the square root. So again, this will go to 4x cubed. Okay, so read through the book, try out the homework, and let me know if you have any questions. Good luck.